Hi everyone, this is Hongkai, and today we're going to continue talking about the probabilistic method in combinatorics. And for this chapter, we're going to talk about the second moment method. And for the first section, we're going to talk about does a typical random graph contain a triangle. We begin with the following motivating question. We call that the Erdos-Renyi graph. Let's say GMP is the n-vertex graph with edge probability P. Which means that for every pair of vertices, there is an edge between them with probability P. And then with the first question, for which P equals to Pn does GMP contain a triangle with probability 1 minus little o1? We sometimes abbreviate with probability 1 minus o little o notation of 1 with with high probability. Or sometimes just simply WHP. In some literature, it is also called asymptotically almost surely or AAS, but we will use with high probability in this in our lecture. By computing expectation of x, which is known as the first moment, we deduce the following proposition: if NP tends to 0, then GMP is triangle free with probability 1 minus little 1. And we can prove it. First, we will let X be the number of triangles in GMP. Then we can know from the linearity of expectation that expectation of X equals to n choose 3. We choose 3 vertices from the n vertices. Then each of them has probability P to have an edge. And then there's 3 possible edges, and so there's a square here. And it's asymptotically to n cubic and p cubic. And given the assumption that NP tends to 0, so this is also tend to 0. Then, by Markov's inequality, we can get the probability of P greater or equal to 1, less than or equal to exponential of x over 1, which is ax. And this is also O1. In other words, we can say that the big X equals to 0 with probability 1 minus little o1. Yeah, and in other words, when P is much smaller than 1 over n, GMP is triangle free with high probability. And because that P, we use this notation, means P is equal to little o notation of 1 over n. What about when P is much greater than 1 over n? We can conclude that GMP contains a triangle with high probability. Can we do that? In this case, we can see that expectation of X tend to infinity. But it's not enough to conclude that P, the probability of X greater equal than 1 is 1 minus little 1. Since we have no ruled out the probability that X is almost always 0, but extremely large with some tiny probability. Important techniques in probabilistic combinatorics is to show that some random variable is concentrated around its mean, and later we'll have one chapter talking about the concentrations of measure. And this will imply the outliers are unlikely. We'll see many methods in this course on proving concentrations of random variables, and it's very common in any other kind of probability course. In this chapter, we'll begin with the simplest method. It is usually easiest to execute and requires no much hypothesis. And then we're going to talk about the second moment method. I think first we should talk about the variance first. We're going to leave some space here. What is invariance? Let's recall it. The second moment method basically shows a random variable is, let's write it down. It shows that a random variable is concentrated near its mean. And our method is to do it by bounding its variance. So we need some definition on the variance. And the variance of a random variable is let's say the random variable is x, is variance of x is defined by the expectation of the square of x minus its mean. And we can expand it, and by some algebra, you'll find that it goes to the expectation of x squared minus the square of its expectation, its mean. And what is the covariance? The covariance of two random variables, let's say x and y, is the covariance of x and y is defined by the expectation of x minus its mean times y minus its mean. And by some algebra, you'll see that equals to the expectation of xy minus the expectation of x times the expectation of y. Yeah, and usually you will use the Greek letter mu for the mean, and sigma square for the variance. And then you can see that usually if a positive sigma will be the standard deviation. And the following basic result provides a concentration bound based on this variance, which is the Chebyshev's bound. First, x is a random variable with mean mu and variance sigma square, and for any lambda positive lambda, we'll see that the probability of the random variable away from its mean is less than or equal to lambda to the power of -2. And it's easy to prove. Let's prove it. Get some space here. It's proved by Markov's inequality. And by Markov's inequality, we can see that left-hand side is equals to the probability of x minus mu greater equal than lambda square sigma square. You can see it's the same. And then we can apply Markov's inequality. Inequality is less than or equal to the expectation of the left-hand side in the inequality, x minus mu square over the right-hand side, lambda square sigma square. And you can see that this one is exactly 1 over lambda square. And it completes the proof, since the numerator is sigma square, which is the definition of variance. And then we'll have a corollary. I have to mention something, that the concentration bound that show small probability of deviating from the mean are called tail bound. And more precisely, the upper tail for x greater than mu plus a, and lower tail for the probability of x less than or equal to mu minus a. And Chebyshev's inequality gives tail bound that decays quadratically. You can see from the right hand side. And later on, we'll see tools that give much better decays. Usually it's exponential, but not quadratically. And if you provided additional assumptions on the random variables, for example, independence. And we are often interested in upper bounding the probability of non-existence, which means that probability of x equals to 0. And Chebyshev's inequality yields the following bound, which means for any random variable x, the probability of it being 0 is less than or equal to variance over square of mean. It's directly from Chebyshev's one. By Chebyshev inequality, we use mu. We write mu to represent expectation of x. Then we'll have that the probability of x being 0 is less than or equal to the probability of x minus mu greater or equal than mu. You can see that this event contains this event, so the probability is bigger than by Chebyshev's inequality. Is less than or equal to variance of x over mu square, and it completes the proof. And we can also have a corollary that if it has positive mean and the variance of x is asymptotically to is little ex squared, then x is positive and x tend to its mean with probability 1 minus little o1. And what does this tilde notation means? It just means that if f tilde g, then f equals to 1 plus little o1 notation g. Okay. Let's go ahead. And then in many situations we found we can see the theorem here. In many situations it is not hard to compute the second moment. We have that clearly the variance of x can be written as the covariance of x with itself. Also, covariance is bilinear, which means that for random variable x1 and x1 to other x and y1, there's no assumption needed to on their independence or anything, etc. And we need some we need a constant a1 and b1, b2, and we'll have the covariance of the sum of the weight x and the weight y. it equals to the sum of over all I and j of ai, bj, the covariance of xi and yj. We are often dealing with x being the cardinality of some random sets. Then we can usually write this as a sum of indicator functions, such as x equals to sum of all the x, and we'll have the variance of x is the covariance of x with itself, and it will equal to the sum of over all I and j from 1 to n, and the covariance of xi, xj from the above equality, and it equals to I minus 1 I equals to 1 to n, the variance of xi summing together, and yeah, you can expand it and get this equation. Yeah, and we'll also have that covariance of xy is 0 if xy are independent. Just in this sum, we only need to consider dependent set pairs, ij. And let's give an example. We'll give an example of some of the Bernoulli independent Bernoulli variables. Dependent Bernoulli. Suppose that x is the sum of random variables, with each xi being independent Bernoulli random variables. With the probability of each xi being 1 is p, and or being 0 with probability 1 minus p. Then we'll have that mu is np, and this variance is np times 1 minus p from some undergraduate, any kind of undergraduate probability course. And if np tends to infinity, then its standard deviation will be little o mu, and thus we'll have that x equals to mu and little o mu with high probability. Note that the above this computation remains identical, even we only knew that the xi's are pairwise uncorrelated. Here you can see that the tail probability decays polynomially in the deviation. Later on, we'll derive some much sharper rate of decays. Let's say we said it before, it will be exponential using some more powerful tools such as the Chernoff bound when the random variables are independent. Now let's return to the problem of determining when the random variable GMP contains a triangle with high probability. Yeah, and we'll have this theorem. If NP tends to infinity, then the random graph GMP contain a triangle with probability 1 minus little o 1. Okay, let's prove it. First we label all the vertices. one by one. So it's by 1 to n. And we will let xij be the indicator random variable of the edge ij. And so we'll see that x sub ij equals to 1 if the edge is present, and also 0 in the other way if there is no edge. It's not present in the random graph. And we can write x sub ijk defined as xij times x sub jk times x sub ki. Then the number of triangles in the random graph is given by the sum over all such ijk, all pairs, times their indicator function. Now we can compute the variance of x. Variance of x. And note that the summands of x are not all independent. And let's say that if T1 and T2 are two 3 vertex sets, then we'll have that the covariance of T1 and T2. It should be the covariance between the indicator function over T1 and T2. That whether there are triangles is the expectation of x sub T1 times the expectation of x sub T2 minus their mean time together, and this one equals to the probability of the little p with the power of the number of edges between the set union of this set minus the p with et1 plus et2. And by discussing cases, we can see, you will see that this one equals to 0 if T1 intersects T2. They have less or equal than 1 common edges. That will be in this case or in this case, and equals to p to the 5th minus p to the 6th. If they have two common vertices, and equals to p cubic minus p to the 6th if they are the same, and the second one will be in this case, and the third one is they are exactly the same. Then we can see that the variance of x is the sum over all T1, T2 of their covariance is equals to n choose 3 times p to the 3 minus p to the 6 times n choose 2 times n minus 1 times the covariance in this case, and this will be bounded asymptotically to n cubic, p cubic, and n to the fourth, p to the fifth, which is little n notation to the n to the sixth, p to the sixth, SNP times 2, 0. Then we can see that the variance of x is little o of the mean square, so that x is positive with high probability by the corollary, by this one. Yeah, and we complete the proof. Here is what we learned from so far. For p equals to pn as n tends to infinity, we find that the probability of GMP contains a triangle equals to, it tends to 0 if NP tends to 0, and equals to 1 if NP tends to infinity. And we will say that 1 over n is a threshold for containing a triangle, in the sense that p grows asymptotically faster than this threshold, which means that p is much greater than 1 over n. Then the event occurs with probability (1 minus the little o1), and if p is much smaller than 1 over n, the event occurs with probability little o1. Note that the definition of a threshold ignores leading constant factors. So it's also correct to say that 2 over n is also a threshold for containing a triangle, but it's not unique. Determining the threshold of a lot of kind of probabilities in random graphs, not only random but also some other random settings. It is a central topic in probabilistic combinatorics, and we'll discuss threshold in more depth later in this chapter.